Range is clear for launch. Firing system armed.
It is May 9th, 1990. The place is Vandenberg Air Force Base in California. Operations Manager Larry Tant is counting down to liftoff of the 113th flight of one of the United States' most reliable launch vehicle systems, Scout.
2, 1, 0. We have liftoff. Scout S-212. Launching 2 MACSAT satellites into orbit.
The mission is a success. Success comes as no surprise to the planners, designers, engineers, and controllers of Scout. Success is the result of over 30 years of striving for letter-perfect performance. The story of Scout is little known outside of NASA circles, but it's a story worth knowing. It's a story of triumph over adversity, of teamwork, and of the pursuit of excellence. In the early decades of the 20th century, the study of flight is the work of the National Advisory Committee on Aeronautics, or NACA. This work is done at the Langley Aeronautical Laboratory in Hampton, Virginia. Langley engineers study the phenomena of drag and of lift. They study the shape of wings and how to cool aircraft engines in flight. Many Langley innovations directly contribute to improvements in airplane design in World War II. In the period after the war, the challenge in aerodynamics is to break the so-called sound barrier. Gathering aerodynamic data at high speeds is a complicated problem. One approach to a solution is to improve the design of existing wind tunnels. Another is to conduct tests of airplane configurations on rockets. These tests are conducted by the Pilotless Research Aircraft Division, or PARD. They are launched from the NACA's Wallops Island, Virginia test facility.
It was basically a technique to verify some of the parameters that were obtained in the wind tunnels of various airplanes in that transonic speed range.
It is 1957. As technology advances and the problems of supersonic flight are resolved, the engineers of PARD are tantalized by the prospect of achieving orbit. Then, the Soviet Union startles the world by launching the first satellite into outer space, Sputnik. This technological achievement startles the world and surprises everyone, including Langley's rocket specialists.
You got to respect their accomplishment in its own right. Disappointed you didn't do it yourself. It forces you to think at a whole new level of exploration and science that heretofore was beyond consideration.
With us, it was disappointment that we weren't there first, of course, but it was also, in a sense, an assurance that we're on the right track, that, boy, we really would get supported from now on, because this was important, and it was obvious that it was important that the United States would continue and try to catch up, and we were part of that game.
The United States responds by mounting a comprehensive program of missile development and space exploration. As part of its response, the nation needs a relatively inexpensive, quickly produced rocket to launch small research experiments. The engineers at PARD are asked to design the new rocket.
Solid-fueled rockets have always had the advantage over liquid fuels as far as simplicity is concerned, and cost, and possibly even reliability. So it was decided that Scout would use all-solid propulsion and would, as a matter of fact, to the extent possible, use existing solid-fuel rockets as the various stages of the launch vehicle. So it was a natural extension of the work that was going on in PARD on solid rockets.
In 1958, President Eisenhower signs the National Aeronautics and Space Act into law. This act dissolves the NACA. Taking its place is the National Aeronautics and Space Administration, the agency that is charged with running the space race for the United States. The need to save time and money means that the rocket must be built with off-the-shelf hardware. Designers select from an inventory of solid-fuel rocket motors produced for the military. The first stage, Algol motor, is a combination of the Jupiter Senior and propellant from the Navy Polaris. The second stage, Castor, comes from the Army Sergeant. And the third and fourth stage motors are designed by Langley engineers who adapt a version of the Navy Vanguard.
Well, it was hectic. It was a frenzy because we were thrown into, especially you got to remember I was a young fellow, we were thrown into something that had never been done before. And we went, approached a lot of dead ends, if you will.
In a way, it was a kind of a race to match the Russians, but more importantly, it was to prove something to ourselves. People did work hard, and they were selfless about helping each other. And there was no distinction drawn between government and contractor people on the job. Everybody was on this team, and they did what they had to do without regard to the color of their badge.
In 1959, NASA Langley awards contracts for control and guidance systems. Chance Vought Aircraft, now LTV Missile and Electronics Group of Dallas, wins the bid on the contract to develop the airframe and launcher. This begins a partnership between NASA Langley and LTV that will last for over 30 years.
We all underestimated the magnitude of the job at that time, but we all had a real positive, aggressive attitude that we would get it done.
In a race against the calendar, this is the vehicle that NASA and its contractors are working overtime to build. In its original configuration, Scout is designed to place 130-pound payloads into a 300-mile orbit above the Earth. It will later be able to carry a 450-pound payload. It consists of 4 solid propulsion rockets joined by transition sections containing guidance, ignition, spin-up motors, and separation sections needed for flight. The heat shield covering the fourth stage and payload section is made of cork and fiberglass laminate. The Scout will fly several missions with an optional fifth stage. Scout stands some 75 feet tall and weighs over 48,000 pounds, a comparatively small vehicle that will accomplish much. The first test flight of Scout takes place on July 1st, 1960. This mission is designed as a probe and carries a 193-pound Langley Research Center payload. The Scout also carries another new feature on board, a destruct capability, to be used in the event the rocket goes off course and endangers populated areas. The launch starts well, yet trouble arises when the radar tracking indicates that the rocket is off course. The range safety officer orders a radio command to destroy the rocket. After reaching an altitude of 860 miles, the first Scout falls into the Atlantic. Only later will the Scout team learn that the failure is with the ground tracking system rather than the rocket.
That was a crushing blow to have destroyed a vehicle that was doing exactly what it had programmed to do. They kicked ash cans and cussed the range safety officer and cried and just went away to be alone and were acted like they'd lost a child.
We wouldn't learn anything if we didn't have problems. And I think that's basic, that's basic in engineering training, is that you try something, and if it works, it's fine. If it doesn't work, you find out what the problem was. This is how we learn. This is the process.
The first fully successful launch of Scout takes place 3 years after Sputnik 1. Carrying a 78-pound probe, Scout Test 2 reaches an altitude of 3,500 miles before returning to Earth. At this point, Scout designers and engineers believe the testing is complete and that the missile is ready to start service. Scout is designed to launch 3 types of missions: to place satellites in Earth orbit, to test heat-resistant materials, and to launch space probes. Scouts are launched from Wallops Island and from the Western Test Range at Vandenberg Air Force Base in California. The infancy of the space age is a time of exhilarating success and heartrending failure. Scout Test 3, the first orbital attempt, fails. 3 of the first 6 flights are failures. In one 5-month period in 1962, there are 3 failures in 4 launches. A NASA investigation finds fault with electrical systems, the heat shield design, and ignition systems.
The Scout program was done in a rush, unquestionably. Everything was running behind schedule, and there was pressure on NASA to perform. The Space Act had been passed, and NASA was supposed to be gearing up to do a job, and Scout was part of that job. And so there was very definitely pressure to do it in a hurry, too much of a hurry, and not enough emphasis on properly qualifying and really getting ready for an operation.
The flight of Scout 110 in June of 1963 symbolizes those problems. At 2.5 seconds after liftoff, a flame appears above the first stage fence. 2 seconds later, the Algol stage is engulfed by fire.
It was obvious that something terrible had happened. You could tell it from the communications of the range safety. There had been a burn through the first stage nozzle, I believe about 15 seconds after takeoff. And the vehicle went through some wild gyrations, and it got about 300 feet high. Broke into 3 parts. The first stage went one direction, the second stage another, the third and fourth fell more or less back on the launch pad and burned. It was a disaster.
I headed up a recovery team the next morning that was out slogging through the salt marsh, gathering up pieces and bits and parts to see if we could put the story back together as to what had gone wrong. And someone had parked a small car inside of one of the assembly buildings. And it just so happened that a flaming piece of green, I guess, had come down and gone through the roof of that building. And it was a small sports car with a canvas top, I guess. And that grain had landed right in the front seat of that car, I guess, and just kind of burnt it to a crisp.
NASA launches another investigation. A 7-man review committee finds flaws in a rocket nozzle, flaws that had gone undetected during production and testing. NASA imposes a 3-month moratorium on the launch schedule to study the launch data. Repeated investigations of the rocket's subsystems reveal that failure is always caused by a different problem. That, in itself, is the big problem.
We never had the same failure twice, but it was clear from the early record of Scout that there were enough miscellaneous failures that we had to sit down and relook at this thing seriously.
And they did things differently at Wallops Island than they did at the Western Test Range. The Air Force had their own way of doing things. The contractor had different ways. And there was a problem with coordinating that.
Back in those days, in the early days of the program, if you needed a part, you would do a little what they call midnight requisition. You would go get the part from the spare vehicle in inventory. Well, that was obviously one of the shortcomings of the system. People were robbing Peter to pay Paul, and in the end result was they had an unsuccessful vehicle.
There simply was not a good standardized vehicle configuration and checkout procedures which were needed to have a successful vehicle.
I remember that I sat down and did some deep thinking about how we ought to take and restructure a look at this rocket, this launch vehicle. And I wrote a specification which ultimately became the spec for the recertification program that was a tiger team approach to completely revising the way we handled the vehicle and standardizing the process to the ultimate degree.
The Scout team mounts an attack on these problems with a 14-month reliability improvement program, a recertification of the rocket. All 27 of the Scouts in the inventory are returned to Dallas to be taken apart and inspected. Weld seams are x-rayed and solder joints are checked under microscopes. Everything is standardized. Test equipment, procedures, even the cable lengths in Vaught's labs will be matched at the launch sites. The launch countdown now covers more than 800 checklist items. Special Tiger teams are formed and assigned to monitor each vehicle processed to enforce compliance with the new standards. No scout will leave Dallas until inspectors make a complete flightworthiness review of the vehicle and give it a clean bill of health. No scout will ever fly again without being certified by this rigorous process of quality control. The passion for reliability, for zero defects, is put to a test on December 19, 1963. The launch of Scout 122R is a success. The relief among the Scout crew is evident.
It's kind of a relief that the pressure isn't on you anymore to go into failure reviews and go into, overtime, weekends, away from your family, things like that. And I think it is very exhilarating.
I think the results speak for themselves. We went on a upward motion of successes.
In a period between 1964 and 1966, Scout establishes a record of 22 consecutive successful launches, and Scout becomes a fully operational launch vehicle. 15 of the 16 recertified rockets are successful.
Now we really had the kind of vehicle that we'd set out to develop, reliable. It was still simple and inexpensive. We could launch them quickly. It took about 6 weeks, I think, to process in the field. And we were launching up to 10 a year with no problem. We were doing the job we set out to do.
Scout's reliability also stems from a sense of teamwork and cooperation between NASA and its prime contractor.
On the program, the Langley staff, which were excellent engineers and were the kind of guys that get consumed by a project, they work hard to accomplish it, they have high ideals and high aspirations. They know how to work with each other to get a job done, and that enthusiasm and that honesty found itself reflected in the contractor's attitude.
We're just a very close-knit, dedicated group, and we had a lot of pride in what we're doing, and we were like brothers.
We were very, very much more liable to work together than we were to work apart. Your counterpart in the government would have a problem or a question. He would contact you on the telephone, and he would be able to say a mutual agreement or solution to that problem. And the end result would be that the program would be much better off for having experienced this degree of cooperation between the two individuals who had the task.
Improvements in rocket motors enable the Scout to carry larger payloads. The Scout's weight-carrying capability increases by several times, while costs remain low.
Now the performance is 4 or 5 times what it was at the beginning. At controlled costs, if you crank in inflation as measured by the Consumer Price Index, a Scout costs less today than it did in 1958.
Taking note of the success and economy of Scout, other countries seek out the Scout to assist them in their fledgling space efforts. The Scout's honor roll includes 23 satellites launched for international space organizations. Payloads are launched for the European Space Research Organization, for Germany, for the Netherlands, for France, and for the United Kingdom. After establishing a record for reliability that includes 37 successful launches in a row, the Scout team celebrates its 100th launch.
The UK-6 spacecraft launch was the 100th Scout launch. And of course it was successful. It was in June 2nd, 1979, I believe.
There was a lot of PR made over it because of the 100th launch. Locally, there were a lot of people that went to see the launch. It was at Wallops. It was a night launch. So there was a lot of fanfare, a lot of notoriety.
Throughout its 30-year history, Scout is involved with many NASA firsts. One of the most internationally recognized projects for Scout is the San Marco project. In May of 1961, Italy and the United States enter an agreement by which NASA agrees to supply launch vehicles, tracking, and training to Italian launch teams. The Italians are to provide the launch complex, personnel, and satellites. The Italians propose an unusual launch site. 2 platforms in Nguana Bay, anchored 3 miles off the coast of Kenya in international waters. This third launch site provides an equatorial orbit to the Scout program.
The reason for choosing to establish this type of launch ring was that the Italian government didn't want to go through the political whatever of reaching agreements with a foreign government to establish a launch base in their territory. But they wanted equatorial orbit. And to achieve equatorial orbit, you have to launch from very near the equator. Eventually, they extended the territorial limit. It was in Kenya anyway, but by then there was no problem.
These people, sitting right there in the Indian Ocean, at least in the early days, 1967, for example, I just wonder how many people in the world had ever seen a liftoff from their front porch, if you will.
This is 5, 4, 3, 2, 1.
This mission, launched on March 25, 1988, is a success, as are all 7 other launches from San Marco aboard Scout.
When we had that string of 37, 38 in a row, it was like being on a winning ball team with no competition. I mean, everybody was just tickled to death, and to add to the success ratio, because we had a few bad ones to overcome, but since research, we had a real good success ratio, and you could actually see the product of your effort in improving Scout.
The Scout became so reliable that mission planners could take it for granted. They focused on the science of the satellite payload rather than its transportation. The pride that Scout people feel about the program comes not only from their successful launch record, but also from the role that Scout payloads have played in the advancement of science. Scout missions study the Van Allen radiation belt that encircles the Earth, and Scout payloads confirmed the existence of the first black hole in space. Early Scout missions involved research into the problems of manned flight in space. To determine which materials could best withstand the heat of re-entry, Scout launched experiments as high as 135 miles, then tilted downward and fired its 3rd and 4th stages toward Earth, so they would reach speeds of 18,000 miles per hour through the upper atmosphere. The output of these missions contributed directly to the later success of Mercury, Gemini, and Apollo programs. The only satellite launched by Scout to ever carry a living thing was placed into orbit on November 9, 1970. The orbiting frog otolith, carrying 2 male bullfrogs, was placed into orbit to investigate the effects of space on the inner ear, to try to understand the causes of space sickness.
Scout is the unsung hero of space. It happens to be NASA's smallest launch vehicle, and it does not receive the same level of notoriety that you would with larger systems. But over the years, it has proven to be a very reliable, consistent performing workhorse for the agency.
Other Scout missions dealt with pure research of outer space phenomena. One mission carried an atomic clock 500 times more accurate than any ground-based time-measuring instrument. This clock was compared to ground clocks to see if it would run faster when further from the Earth's gravity. This mission confirmed Einstein's gravitational and relativity theories of 70 years earlier. Scout also launched the Navy's transit satellites, which provide accurate navigation to the fleet and to over 6,000 commercial enterprises and foreign countries. In the late 1970s, NASA's policymakers decided to launch all future NASA satellites on the Space Shuttle and abolish all expendable launch vehicles. But the failure of Challenger in 1986 reversed that policy. While the shuttle was grounded, it was obvious that the space program needed more launch capability. In response, NASA established the mixed fleet concept. Under the new plan, NASA will obtain launch services from commercial firms to launch government payloads. These directives mean changes for Scout.
The program as we know it is ended, essentially is what it means. The fact that there's so few vehicles left doesn't give the Vought people and the Goddard people a time to develop the same type of a working relationship as we did. And then once those 5 vehicles are gone, it's back to the launch services concept. So the launch vehicle business, as we knew it, is essentially ending.
On January 1st, 1991, Langley turned the Scout program over to NASA's Goddard Space Flight Center. LTV Corporation will continue to market Scout as a commercial launch vehicle. Goddard will launch the remaining government-owned rockets. This salute to Scout at Langley marks the end of an era, and it gives veterans of the program a chance to remember.
We all had one common goal. The teamwork also was a result of mutual respect for each other. It wasn't an adversary type situation where it was always knocking of heads. It was strictly a job that had to be done and done in the most reliable manner.
I don't think there's ever been another project where government and contractor people work together as closely as they did on Scout. Partly, I guess it was the nature of the program, the goal, the job that we were charged to do. I mean by that it was to be an inexpensive rocket used by a lot of people. It was a goal that you could put your heart into.
There's something about the program. You work it for a little while and you get involved in it. And then when that happens, you lose the lines of, whether you're agency or whether you're LTV or whether you're Air Force, you become a Scout person.
Scout's success rate of 96% has earned this workhorse a spot in the National Air and Space Museum, where it stands beside other veterans of America's space program, such as Jupiter, Aerobee, and Vanguard. Over 700 people have worked on the Scout program during the past 32 years. These Scout people created a launch vehicle that set a standard for productivity and reliability. They established uncompromising standards of exactness. They set records for success. They were unwavering in the pursuit of excellence. And in accomplishing these things, they created an atmosphere of teamwork and mutual respect that all of those who worked on Scout will never forget. The NASA space program has given us images that have become imprinted on the national consciousness as icons of success. Here is one more to consider: the unsung hero of space.